Good day everyone, this is Engineer EMV and welcome to my channel. Before we proceed, hit the like button and subscribe for more civil engineering topics and practice problems in my channel. So this will be our first practice problem regarding the area under the curves using integral calculus. So problem 1, we need to find the area bounded by the first quadrant, the curve x squared y is equal to 8, and the lines x is equal to 4 and y is equal to 8. Recalling our first step in solving, we should graph our curves and our lines. So I have here the first quadrant region of the Cartesian plane. So next we are going to plot the points of the curves and the lines. So this is a tip. We can use our mode table function of our calculators to make our plotting easier. So mode table and f of x is function of x. It means that our equation should be in the function of x. The left side should be equal to y and the right side should be equal to x. So y is equal to 8 over x squared by transposing our values. So f of x now is equal to 8 over x squared. By entering it in our calculator, 8 divided by x squared. Start value, it means that this is where our plotting will start. Let it start at 0. It will end at 6. And the step is the interval. We set it as 1. And as you can see, there is a table, x and f of x, or x and y. Let us plot one by one. So we start at 1. 1 corresponds to an ordinate of 8. So this is the first point. And the abscissa 2 corresponds to an ordinate of 2. So by looking further at the values, we can observe that the behavior of the curve is in this manner. So that is only approximate, but it can do. This is our curve y is equal to 8 over x squared. Next, we need to plot our line. So x is equal to 4 is simply a vertical line passing through x is equal to 4. And y is equal to 8 is a simple horizontal line that passes through y is equal to 8. So the area that we are looking for is this region, since it is stated in the problem that we should find the area bounded by the first quadrant and the following curves and line. Next step is to determine the points of intersection. So to determine the points of intersection, we can equate our curves and our lines. So in this case, this is our point of intersection. So we can equate the curve and the line x is equal to 4. So let us find this value of the point. So we equate the curve y is equal to 8 over x squared to x is equal to 4. So let's substitute our values. Y is equal to 8 over 4 squared or equal to 0.5. So we can say that this point of intersection is 4 and 0.5, and this is obviously 1/8. So we have 1/8 and 4 0.5 as our points of intersection, and we will use this as our boundaries or our upper and lower limit. So the third step is to analyze what strip are we going to use. So if we are going to use horizontal strip, it is okay, since in this part, the endpoints of the strip is in two different lines. But as it goes down, the other endpoints of the differential strip will change from one curve to a line. So we can also use vertical strip. So in this part, we are going to have a different endpoints of the differential strip. So as it goes to the right side, one endpoints of the differential strip will change from the line y is equal to 8 to the curve 8 over x squared. So it means that we can solve it by considering two different areas. So this will be area 1 and this is area 2. So you can notice that area 1 is in a rectangular in shape. By isolating it, area 1 is a rectangular that has a dimension of 8 and 1. based on our plotting of points. So area 1 is equal to 1 times 8. Area 1 is equal to 8 square units. Now, this is our area 2. We take a vertical strip that represents the differential area of the curve. So we measure it from the positive x-axis. It will be called as y. So let us isolate our strip. Since we are using vertical strip, our width is dx and our length is y. So differential area is equal to y dx. Area is equal to integral of y dx. We don't have any other values of y like our y outer, y inner, since we only measured one curve from the positive x-axis. Now, inputting our values, a is equal to the integral of the y that we are going to use is the value of y of the curve. So it is equal to 8 over x squared dx. We can now proceed to the integration since it is in the function of x. We should now get our limits. In solving for area 2, the limits is from, since we divided our total area into 2, the area of the second region will start from the termination point of the first area. So it will start from 1 and up to 4. So let us now calculate the values. Integral of 8 divided by x squared from 1 to 4. It will be equal to 6. So solve for the total area, we simply add the area 1 and the area 2. So the total area is equal to 14 square units. And that is how we solve areas under the curves. Stay tuned in my channel for more practice problems on area under the curves using integral calculus. That's all for this video. I hope you've learned something, and if you have questions, inquiries, and topics in mind, just comment it down below, and let's see what will be our next topic in our next videos. Don't forget to hit the like button and subscribe for more civil engineering topics and practice problems by Engineer EMV.